Hello there, it's time to start. Hello, welcome to my presentation about unmanned autogyros and about ThunderFly TF-G2 autogyro, which is controlled by PX4 Autopilot. I'm Dvořák and I'm a member of the ThunderFly team. ThunderFly is a Czech company that focuses on development and production of unmanned drones and avionics. Autogyro is not a well-known thing. It's a type of aircraft that is heavier than air, and it's flying by a free spinning rotor that produces lift. Autogyro was nicely illustrated in XK CD comics, so we can read it together. Autogyro looks like a helicopter, but it's nothing like helicopter because it has a rotor on top, but this rotor is not powered and is free rotating. Control of autogyro is much easier because it's controlled by moving, tightening the entire rotor plane, and the setting of rotor blades is fixed. Big blade on the top is not powered and spins freely, it's clear. Flies like a plane, but is nothing like a plane. Yes, it has propeller and some engine that pulls or pushes the autogyro forward. This forward movement rotates the rotor. Autogyro is sort of like a powered parachute. Autogyro is capable of unpowered autorotation, which is good in some case of failure of avionics or of some actuators. Need a runway to take off, but not a long one. Autogyro is safe unless you do one thing instinctively. Due to escape stall in a normal airplane, in which case it will crash immediately. It's a problem for manned autogyros with pilot on board. Autogyros with autopilot can be programmed and they avoid it. Until autopilots will not be based on artificial intelligence, fortunately, this is not the case of PX4 autopilot. It can land vertically, it cannot hover, and never stalls. Autogyro was invented by a Spanish civil engineer, Juan de la Cierva. Juan de la Cierva was interested in airplanes, and he assembled several aircraft himself. After some crash of his airplane due to stall, he decided to invent something that is safer than standard plane. He wanted to build a safer airplane. His demands were able to fly in low speed, able to fly safely in low altitude, good controllability regardless of speed, and independent on power unit. His first flying autogyro was built in 1923. It was Autogyro C4, and first circular flight was long 4 kilometers, and it took 3.5 minutes. And how autogyro work? The principle of an autogyro is quite simple. In general, forward speed is obtained from a motor with propeller. This power unit can be in drag or in push configuration. The rotation of the rotor creates lift and drag that carries the mass of autogyro, surrendering airflow from forward movement ensures that rotor is spinning at sufficient speed. And how is autogyro controlled? It's also quite simple. Roll is controlled by titling rotor plane to the sides, and pitch is controlled by power unit of motor, and by titling rotor forward and backward. Autogyros are usually equipped with a rudder that eliminates torque of the rotor and motor. Now I would like to compare some key parameters of these platforms, of autogyro and of other common platforms with multicopter, helicopter, and plane. The easiest takeoff has multicopter and helicopter because they can take off from place. Vertical takeoff. Plane and autogyro need some distance to take off. Some small disadvantage of autogyro is that rotor mass spins before takeoff. Therefore, it's not possible to start by some catapult. Forward movement is used to reach takeoff RPM of rotor. Safety mode. Multicopter have parachute. Is only this option. Helicopter and autogyro can do some controlled auto-rotation, but helicopter must enter in this flight mode. And I don't know autopilot that can it or know how to enter to this auto-rotation. A plane can glide somewhere by some pattern flight. Hovering is possible with multicopter or helicopter, but plane and autogyros are inherently stable, and they are absent downwash. Unpowered flight is impossible with multicopter. It will immediately crash without power. Helicopter and autogyro can descend in auto-rotation, and plane can glide. Autogyro is at least sensitive of these all platforms to weather as wind gusts, and the plane is the most sensitive. Here is comparison of some performance in real weather conditions and cost of the platform, cost or complexity, mechanical complexity. Autogyro is in the middle. Helicopter is have better performance, but it's more complex and difficult device. Autogyro is have much better performance in bad weather conditions. Why did we started with development of autogyro? We needed a platform that will be able to fly in bad weather condition, and which will be able to do some aerial work. For example, some measurement of some parameters of atmosphere. Our requirements for that UAV was able to fly in wind gusts or in some rain, simple to control, simple to pilot, safe in case of some failure of avionics or in failure of some mechanical parts, and with a minimum of mechanical parts. After exploring all options and available platforms, autogyro was selected as a good compromise. Autogyro is good because it is resistant to hard weather conditions, wind gas or bad weather, high precipitation, snowing, raining, and so on. Autogyro is able of take off on a short runway, which is good if we want to take off in a place with bad terrain on the ground. TF-G2 is possible to start by drawing from the hand or from some moving platform, for example, from moving car. We also tested the start on the rope as from the winch. Autogyro is always in auto rotation mode, and it is also safety mode. So the change between normal flight and this safety mode is very simple and quickly. Autogyro is also very simple. It contains only a few mechanical parts. We definitely needed to be unmanned and to be able to fly automatically. When we started, we didn't know any other autonomous autogyro project, especially there is minimum information about autogyro controllers and their implementation. Next step is that we needed to choose and select some autopilot. There are several ways to how to choose. Developed own controller, it's not a good way because it's not sustainable for the future and for long-term development. Proprietary autopilot, it's an also option, but in any issue with incompatibility of platform and that autopilot, it's very difficult to solve it. It's not suitable for development of a new platform or on a proprietary autopilot. Open source autopilot, it was an optimal way for us. There are several open source autopilot, and after reviewing the possibilities, we decided for PX4 autopilot. PX4 team looks very helpful to improve and give support for developers, and the structure of PX4 code is nice because developers keep it in a flat maintained development tree, and all features are in one branch. Then we started to figure out how to get started. We had no experience with autopilots, with PX4, with autogyros at the beginning. We started with following of documentation of PX4, and we created first airframe for RC model Autogy2. It was our first flying autogyro at all. Autogy2 is a commercially RC very light model which needs some modification. We mounted autopilot into it, and we made some improvement of existing parts using 3D printing. But it wasn't enough for us very quickly. In the time of the lockdown in the Czech Republic, we continued with development, and we designed a new autogyro from scratch, unmanned autogyro ThunderFly TF-G2. Autogyro TF-G2 was designed as open source project. All construction parts are drawn in open source 3D CAD software, OpenSCAD, and are available on GitHub, except for common mechanical parts as bearings, screws, and so on, and some avionics and electronics, autopilots, motors, sensors, servos, and it's almost free completely 3D printable. It's controlled by a PX4 Autopilot, and the 3D printing provides us a way to very fast development, and it's very easily modifiable. The original intention was to create an autogyro for training pilots of bigger unmanned autogyros. Learn how to operate RC, how to command Autopilot, how to control ground control station. And due to smart design of it and highly parametric design, it is able to do some work, some aerial work, and carry some micro payload. It is able to carry up to 100 grams. It is enough for some sensors or some payload. On this side, you can see some highlights parameters of our autogyro. Weight is up to 1.5 kilometer. In air, it can fly up to half hour, and trajectory distance can be up to 25 kilometers. It is very easily repairable due to 3D printing and open source, and construction is designed in open source license. It supports automatic fly provided by PX4 Autopilot. It's possible to launch from hand or from car roof. Rotor diameter is from 80 centimeters to 1 meter and 5 centimeters. Takeoff and landing is possible in crosswind up to 15 meters per second, and it's resistant to wind gust up to 10 meters per second. Airspeed flight range is between 7 and 25 meters per second. During the development, we faced the need to modify certain parts of software and hardware, or develop new electronic sensors. It begins with development. It begins with need to know a revolution of the rotor. Therefore, we developed own I2C RPM counter with a probe that is possible to mount into the autogyro or any drone. This RPM sensor, TF-RPM, is a PX4 firmware. Drones are usually using pitot tube for measuring airspeed, but the pitot tube is not sensitive at a low speed, below 10 meters per second. And it's very easily clogged by some dirt, for example, after some unsuccessful landing. Therefore, we designed an airspeed sensor that is based on Venturi effect, Venturi tube. We call it TF slot. It's possible to see here. It is standalone version, and here it is mounted in our TF-G2 pylon. Here is rotor mounted. This sensor is based on a differential pressure sensor, and because equation for calculating real airspeed from measured different pressure, we needed to modify profile in PX4 firmware for right calculation. We were having a problem with available GPS receivers that were not very well resistant to EMC noise. Attempts to shield it from avionics did not help much. The solution was to design own multi-constellation receiver that supports GPS, Galileo, GLONASS, and BeiDou. With high-quality shielding, high-quality filters, and high-gain antenna. We need to log some data from payload on board. It is next our pull request, and currently we are working on automatic takeoff mode for Autogyro. In order for every user to be able to launch Autogyro, not only TF-G2, every Autogyro, we are trying to automate start for autogyros. We have developed a takeoff assistant that tells that autogyro is ready to start, but it was only assistant, and now we are working on completely automatic takeoff. The next challenge was to obtain high quality and high reliable telemetry link. Now I would like to show you a short video that show us our work, our autogyro, how it is possible to start, and how it is flying. Here you can see start from the hand by drawing it. The man can recognize that RPM of rotor is sufficient for safe takeoff. Now TF-G2 is mounted on platform for takeoff from the roof of moving car. Before takeoff, rotor must be rotated, and here is launch from roof of car itself. Okay, so as I said earlier, the design of the autogyro is completely open source and available on the GitHub. During the development, we found that it is very difficult to have quality and repeatability quality of 3D printed models by slicing it in graphical user interface of slices. And the quality of printed part very depends on the setting of slicer, and it also varies between versions of slicers. Therefore, we have developed own procedure or workflow that renders and slice all source data from OpenSCAD files to G-codes for certain printers. It's not very recommended to slice files yourself by some general slicer, because it can be dangerous to fly with these printed models. We have created own print configuration for some groups of parts for certain printers. For example, some parts need to be accurately balanced, and the change of amount of infill can break this balancing of models by right slicing, because it's quite hard We provide for community access to our G-code for some improvement or fixing of bugs or issues. How to do it? The way is quite straight, and you know how to do it for sure. You need to fork our TF-G2 repository, solve issue, commit it, and make pull request. And against of this pull request, you obtain the G codes that are slides with the right configuration and which are somehow verified that the result of printing will be enough quality for flying with it. That's all from me, and very thank you for your attention. If you have any question, ask us or leave me or us some message, email, what you prefer. So I try to look to questions and answers. Here's one question. How the vertical auto rotation looks like? Vertical auto rotation is slowly decreasing of altitude because the air is coming through the rotor plane, and it speeds up rotor RPM, and it provides us sufficient lift, and it carry mass of body of autogyro. The speed of vertical auto rotation is about 3 meters per second. So it's quite good value for some safety mode. Yes, Matthew asked for descent rates in fail-safe mode. It's about 3 meters per second. Any other question or interest? You can write us some message if you want. So it looks like it's all. No. What is PTHE owner required to flight? I don't know what is PTHE. What is power required to fly? For Autogyro TF-G2, it's around 300 to 400 watts for a straight flight. TF-G2 is usually powered by batteries with 5,000 mAh, and it's for 4 cells batteries. Okay, 1 minute to end of session. Any other question? I hope that I answered questions. So it's time to end. Thank you very much for your attention and question, and bye.